Welcome back to the channel. In today's video, we will cover the second part of our two-part series on the calibration curve, which is part of our larger fundamentals of analytical chemistry series we're undertaking right now. And the goal of this video is to demonstrate how we can adapt our method that we built in the last video to build this calibration curve to either take in a new single value or a list of values. And practically this is important because oftentimes in the analytical context, you might have multiple samples that you now want to predict the concentration for from the same calibration curve. And so I want to demonstrate how we can add some flexibility to that method. In part one, we had a sample list of X values, which represented maybe the concentration of known samples, and Y values, which could be the experimental measurement. And so we have a calibration set of data. We then use the linregress method, X and Y as our values, to predict MB, R-val, P-val, and standard error. So these are the model parameters, M and B here. And so next, we could take a new Y value, some unknown sample that we've now taken a measurement for, and then use that to get X predicted, the predicted concentration of that new sample. So here we've extended this idea into two functions. The first function is build calibration curve, which takes in two lists, a list of X values and Y values. We generate that same list of parameters. We store them as a dictionary so that our second method, called solve for X, can take in a new Y. So again, that's that new sample, the curve parameters. It then looks at M and B from the curve params and then returns a predicted X value. And you can see that here. So here in part two, I'm showing an updated figure where if I have a new sample that is measuring with an intensity value of 8 and I use this calibration curve, the predicted concentration is 4. If we update this to a new value such as, let's say 6.2, we run this cell and you see that we now have a predicted concentration of just above 2. So now in this video, I want to demonstrate how we can modify solve for X to not just take in a list. And so in this case, if I have new Y's, a list of Y values, maybe this represents 4 samples, or a single value, whereas now an integer, our method can discern the difference and then still either return a list of new X concentrations or a single value for our new Y sample. So the first thing I want to do is copy this function and start, and we'll just call it solve for, let's just say X's. And it will take in some Y value. The curve parameter stays the same. The M and B will stay the same, but we're going to add a little bit of extra in the middle to check the type of value for new Y. So to do this, we're going to use a method called isinstance. And let's take a look at how this works. If we look at new Y and determine if it is a list, we pass in an object and evaluate it against a particular data class, this will return false. However, if we look at new Y's, this list here, and make this comparison, you see that it returns true. And so we can use this idea of evaluating the type of data in order to determine which path we want our function to go down. And so in this case, let us first evaluate the instance of the data type and then make an assessment. So let's do that. So if is instance, and instead of Y, instead of new Y, let's call it vals. And we're going to say if instance vals is a list, then we're going to do something special. We'll say for val and vals, we're going to leverage this equation, and I want to create a new list called X preds. So predicted X values will be an empty list. So then I will append X preds, dot append, and we'll append this equation. And instead of that, we'll just pass in val. So as this loops through, val becomes representative of Y values, and then append those values to X predicted. And then we will return X preds. Let me make sure that's tabbed correctly. And so if we have a list, it'll go down this path, run this for loop, and then return the value. Else, if we don't have that list, then simply return vals minus B divided by m. And so this is that original equation that we had. And if we run this, we should now have a method that can take in single values or multiple values. And so let's say we have a concentration for new y. Oh, let's see what we've got. Oh, and I pass in my params. And so our equation is 8. We've already looked at 8 before, so we know that 8 should equal 4. And so that looks good. And now if we switch it to new y's, you see that we now get a host of values for 5, where an intensity value of 5 gives us a concentration of 1, intensity value of 7 gives us a concentration of 3, and so on for this list. And now we have a more flexible way to evaluate either a single sample or multiple samples. So I hope this allows you to see how we can now take a lot of this work and maybe even now build apps to do many of these calculations now that we have functions, and some of which are quite robust for this type of analysis. If you want to see how we can do that, subscribe to the channel and I'll begin looking through many of these that we've done for ANOVA, t-test, and visualization, and how we can build that into a stats app targeted at analytical chemists. If you enjoyed the video, like, comment, subscribe, and I'll see you in the next one. Peace.